The United States military's ability to fire a single weapon relies entirely on a microscopic layer of an obscure metalloid. That material is antimony. The Department of Defense classifies it as a Tier 1 critical mineral, a resource deemed absolutely essential to national security, but highly vulnerable to supply chain disruption. You will find it packed inside every ammunition primer, alloyed into every armor-piercing bullet, and embedded in the sensors of every night vision goggle in the U.S. inventory. Despite requiring thousands of tons of this material to maintain combat readiness, the United States currently extracts exactly 0 primary antimony from its own soil. In December 2024, the primary supplier abruptly severed the pipeline. Citing national security interests, the Chinese government enacted a complete targeted embargo, banning all exports of antimony to the American defense sector. The global spot price for the mineral spiked by 300% within weeks. Meanwhile, the U.S. National Defense Stockpile held barely 1,100 tons, a fraction of the roughly 24,000 metric tons the nation consumes annually. The Pentagon's $800 billion budget cannot bypass this bottleneck. As this graphic breaks down, the defense industrial base relies on 3 distinct chemical forms of antimony: metal, trioxide, and trisulfide. There are no scalable substitutes for these compounds because the military's dependency is hardwired into the laws of physical chemistry. Inside the primer cup of a standard cartridge, antimony trisulfide acts as a mechanical sensitizer. When the firing pin strikes, those sharp, needle-like crystals are violently crushed against the primary explosive, creating the microscopic friction to spark the energetic train. This chart maps the specific thermodynamic curve of that reaction. As the localized temperature rises, the compound hits 548 degrees Celsius and undergoes endothermic melting, a process where a substance absorbs intense heat from its surroundings to change from a solid to a liquid. This liquid pool acts as a vital thermal buffer, transferring a sustained heat to the main gunpowder charge without causing the propellant to shatter. Attempts to use non-toxic substitutes, like bismuth sulfide, fail at this exact stage. Bismuth sulfide melts at 850 degrees Celsius. That massive thermal discrepancy alters the required activation energy, preventing the formation of the liquid slag and leading to catastrophic misfires. Down the barrel, the physics are equally unforgiving. At 60,000 pounds of pressure, a pure lead core would compress, melt, and strip the steel rifling. This diagram illustrates how metallurgists solve that problem by creating antimonial lead. By alloying 1 to 6, they physically pin the lead's crystal lattice in place, preventing plastic deformation under extreme stress. Looking at this bar chart of Brinell hardness, a standard measurement of a metal's resistance to denting, we see the direct result of that dislocation pinning. The addition of just 6% antimony causes a 140% jump in the core's structural rigidity. This specific hardness profile ensures that armor-piercing rounds survive the violent acceleration of firing and maintain their geometry to penetrate heavy target plating. The lethality and mechanical reliability of the weapons carried by U.S. infantrymen are strictly dictated by these microscopic, irreplaceable metallurgical manipulations. At the aerospace level, the chemical application shifts to target acquisition. Indium antimonide is the foundational material powering advanced sensor suites on combat aircraft. Indium antimonide is a specialized semiconductor alloy engineered to react strictly to mid-wave infrared light. It is used to manufacture cryogenic focal plane arrays, grids of heat-sensitive pixels chilled to extreme temperatures that form the core of modern thermal cameras. These arrays translate invisible thermal photons directly into glowing electronic targeting data. This precise optoelectronic conversion process is the core technology that allows infantry night vision goggles and drone targeting pods to operate in zero-visibility environments. When those same aircraft are targeted by heat-seeking missiles, survival relies on the automated deployment of decoy flares. This line graph of radiant intensity demonstrates how antimony trisulfide provides the necessary quantum mechanics to spoof modern weapons. When the flare combusts, the antimony oxide molecules release photons specifically in the 3 to 5 micron wavelength. The pink spectral line perfectly overlaps the dashed jet engine peak, computationally tricking the inbound missile by mimicking the exact exhaust signature of the aircraft. Antimony executes kinetic strikes, tracks enemies in the dark, and ensures survival inside contested airspace. To sustain this global architecture of munitions, sensors, and countermeasures, the U.S. defense and industrial base consumes roughly 25,000 metric tons of antimony every year. However, 90% of global mine production is locked within the borders of China, Russia, and Tajikistan. Facing a severed supply chain, the Pentagon invoked the Defense Production Act, a federal law allowing the government to force private companies to prioritize national security contracts. The Department of Defense is now injecting hundreds of millions of dollars into domestic extraction projects, like the Stibnite Gold Project in Idaho, alongside specialized smelters to rebuild the pipeline. But a supply chain cannot be printed on demand. Environmental permitting, the construction of complex metallurgical facilities, and the establishment of secure refining nodes will take years of sustained effort to bring online. The United States engineered the most sophisticated kinetic and electronic warfare apparatus in human history. By building that apparatus on a foundation of foreign-sourced minerals, the nation left its tactical supremacy entirely at the mercy of its primary adversary until the supply chain is physically reshored.